Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized pieces.
Today, we're diving into the world of artificial intelligence and chemistry, specifically how we teach an AI to read the language of molecules. You might think of a language model like ChatGPT, which is great with English, but chemistry has its own language with its own alphabet and grammar.
Exactly. And a computer can't just look at a drawing of a molecule. We have to translate it into a line of text first. One of the most common ways to do this is a system called SMILES, which stands for Simplified Molecular Input Line Entry System.
It's a bit like chemical shorthand. For example, the SMILES for water is just the letter O. For ethanol, the alcohol in drinks, it's CCO. It's a clever way to represent a complex 3D structure in a simple text string.
So once we have our molecule written out as a SMILES string, the AI needs to read it. But just like we read sentences by breaking them into words, the AI needs to break the SMILES string into meaningful pieces. This process is called tokenization.
And that's the central question of the paper we're looking at today, titled Where to Cut, How Deep? BPE and Unigram-LM on Chemistry SMILES. It asks a really fundamental question. What are the words of a molecule, and does it matter how we define them?
For years, scientists building these chemical AIs have mostly just borrowed a tokenization method from human language models called BPE, or byte pair encoding. They didn't really stop to ask if it was the best way, or even a good way, to do it for chemistry.
Let's quickly explain the two methods this paper looks at. First, there's BPE, the popular one. You can think of BPE as a builder. It starts with the absolute basics, the individual atoms and symbols. It then scans through millions of molecules and finds the pair of symbols that appears together most often, say a carbon atom next to another carbon atom, and it decides to merge them into a single new word or token.
It keeps doing this over and over, always merging the most frequent pair. It's a bottom-up approach that's very greedy. It just wants to build bigger and bigger chunks out of the most common building blocks it sees.
The other method is called Unigram-LM. If BPE is the builder, Unigram-LM is the editor. It starts from the opposite direction. It begins with a massive, messy vocabulary of every possible chemical chunk you can imagine. Then it carefully goes through and starts deleting the least useful or probable chunks.
It prunes the vocabulary down, top to bottom, until it has the most efficient and statistically likely set of words to describe the molecules. It's less about just finding the most frequent pairs and more about finding the best overall dictionary.
The big question was whether these two very different approaches would basically end up in the same place when applied to chemistry. The language of chemistry is much more rigid and rule-based than English, so maybe, despite their different methods, both BPE and Unigram-LM would be forced to discover the same important chemical chunks.
To find out, the researcher ran a very careful, controlled experiment. They took both algorithms and made them build their chemical dictionaries from the exact same starting alphabet of 165 basic symbols. Then they fed them huge datasets of molecules to learn from, one with all sorts of diverse chemicals, another with just drug-like molecules, and a third with natural products.
Then they compared the dictionaries that BPE and Unigram-LM came up with, and the result was stunning. They were not the same. They weren't even close.
The paper describes them as near disjoint. That means the sets of chemical words they learned barely overlapped at all. The overlap was less than 16%, and when they looked at the most important words, the ones an AI would actually use most often, the overlap was less than 5%.
It's like asking two people to invent a language for chemistry, and they come back with almost completely different dictionaries. BPE, the greedy builder, learned to create big, chunky tokens. It loved to take common structures like the carbon rings you see in lots of medicines and make that whole ring a single word or token.
Whereas Unigram-LM, the careful editor, preferred to keep things small and fine-grained. The paper has this fantastic image comparing how they see the nicotine molecule. BPE breaks it into a few large pieces that span whole rings. Unigram-LM breaks it down into what looks like a scatter of small beads.
This leads to the second major finding, which the paper's title perfectly captures: where to cut, how deep. It turns out both algorithms mostly agree on where the natural breaking points are in a molecule.
But they completely disagree on how deep to make the cut. Unigram-LM makes lots of shallow cuts, creating many small pieces. BPE comes along to those same spots, but makes one big, deep cut, grouping all those smaller pieces into a single, coarser token.
And what this means in practice is that for the exact same molecule, Unigram-LM will produce 30 to 40% more tokens than BPE. The AI gets a longer, more detailed sequence of smaller pieces to analyze. With BPE, it gets a shorter, more compressed sequence of bigger chunks.
And this wasn't a fluke. These differences held up no matter what kind of molecules they were trained on, or what size the final dictionary was. It's a fundamental algorithmic difference in how they perceive chemistry.
So why does any of this matter? It sounds like a pretty technical detail.
It matters because it shows that the choice of tokenizer is not a trivial step you can ignore. It's a critical decision that fundamentally changes how the AI model is going to read and understand a molecule.
An AI trained using BPE's dictionary is learning about large common functional groups and scaffolds. An AI trained using Unigram-LM's dictionary is learning about much smaller, near-atomic interactions. Those are two very different ways of seeing the world.
This paper doesn't claim one is better than the other for downstream tasks, like designing a new drug or predicting a molecule's toxicity, but it proves for the first time in a really rigorous way that they are profoundly different.
It moves the field from a place of using an inherited default to a place where scientists have to make a conscious choice. They now know that the very first step in their process, how to chop up a molecule, is a real impactful decision that needs to be justified. It's a fantastic piece of foundational work that says, hey everyone, we need to pay attention to this.
It really is. A great reminder that sometimes the most important questions are about the foundations we thought were already settled. That's all the time we have for today. Thanks for tuning in to Daily Papers.